Hey Pre-Calculus, here we are in section 4.8, the last section of chapter 4, and we're going to be talking about modeling real-world data with polynomial functions. There's no real vocabulary today, but it would be a good idea for you to refresh yourself with the idea or the visual of what certain types of polynomial functions look like. So we know the linear function looks like a line and there's no changes in the movement. And we know that a quadratic we can have, and I like to call them happy and sad quadratics. You can have a quadratic that has this kind of change in direction goes here, then there's one change, or you can have this kind of a quadratic parabola situation. And you've got, cubics and quadratics, which shows the number of changes that we could have in terms of the direction. This is going to be important for us to kind of qualify the data and figure out how to organize our information. So when you have a situation like this, if you're given data and the data points seem to fall in a particular way, mathematicians like to use that information for predictions. We've done that with linear equations in pretty much every class, Algebra 1, Algebra 2, even pre-calculus. But now, given the fact that we have information about polynomial functions, we should be able to not restrict our data just to linear situations, but we should be able to say, hey, this looks like it could be part of and your job is to determine the type of polynomial function that could be used to represent the data, and that would be, in this case, a cubic, right? You can see the number of changes in direction, 1, 2, we've got one change because we go from here to here, and then 2, so 2 changes that we see, and indeed, that would be cubic. And here, hopefully you're seeing that this looks somewhat parabolic, and so you can see that this looks like a quadratic. So how do we use this information? Well, let's say you collected information like this and you wanted to try to figure out if there was some kind of an equation that you could use to represent or retrofit the information. First thing you want to do is take the data and model it in a graphing calculator or some kind of a graphing app. So when we get to Desmos, you're going to go over and add this table. And after you add the table, we can put information right into the table and see if we can figure out how our Desmos app will give us an equation or retrofit an equation to the data. So after I plotted those things in, I'm over here at Desmos, and you can see that we get this shape, and you can see that it looks really like a polynomial that's a cubic. So what I'm doing here is I put in this generic cubic equation, except instead of using an equal sign, I use a tilde, which is right by the number 1 on your keyboard or most keyboards. And so you use the tilde instead of the equal sign. And then since we are dealing with x sub 1 and y sub 1, we are going to use that in our equation. So what this is called is, I keep saying reverse engineering, but that's not what this is called. What this is called is regression. So if this were a linear equation, it would be linear regression. This is a cubic equation, so this is cubic regression. So what you do is you put a generic type of equation in the form that you want. Because we're looking at this, we're seeing it's a cubic. You make sure that the variables you have are referring to the variables that are there in your table. So I have to make all of these x's x sub 1s, and I've got to make all the y sub 1. And then you scroll up and you can see that they've given us values for A, B, C, and D to fit the data we have. And honestly, it fits it really beautifully. So now it's time for me to write my equation. So I slide over here. F of x is equal to x cubed because that a value is 1. Our b value is negative 3.00163. So I'm going to put that in there. 3.00163 x squared. Now I'm looking for the c term, which is going to be the x term, and then I need the constant. So I run back here, I take a look, 1.009. I'm going to put that in there. That's positive 1.009. And then finally, my constant term is going to be negative 5 5.00163. I don't remember. 186. All right. And that is how you do it. All right. Not a whole lot of work on your part, but make sure, guys, you understand how to use whatever device you're using. There's different regression forms if you're using like a TI, a Texas Instrument calculator. And so if you need help with that, let me know. So here in example 3, we get to use the polynomial equation that we create. Now this was based on a problem earlier in the text. It shows that the average daily amount of waste generated by each person in the United States during from 1980 to 1996 is listed below. This includes all waste such as industrial waste, demolition waste, etc. And so you can see our chart gives us some information. What we're asked to do is to write a polynomial function that can be used to model the data. Then we're asked to use the polynomial function for prediction purposes. And that's really the reason why mathematicians gather data, try to find an equation that fits the situation, so there's prediction that can be done, so we can use that data to kind of help us get information. So let's get started. We're going to go back over to Desmos. So here we have the data plotted, and I've zoomed in a little bit just so it can look a little bit better, because when we were zoomed out, it doesn't look like much, looks like a pretty sad line. But if we're talking about polynomial situations, what kind of a polynomial would this be? It could be some of anything. It could be like so many changes, or you could, look at it as perhaps trying to figure out if there's a linear regression that could happen. But the fact is, this is distinctively going down. We've had a trend downward, so maybe that trend will continue. This is the plight of a mathematician. This is the plight of a data analysis, trying to figure out what's happening with not that much data. I'm sure if we had like a little bit more, maybe some information between the 80s, a little bit more during the 80s, we might be able to get a better feel. However, what we're going to do is look at this as a quadratic equation. We're going to use a quadratic regression to represent this information. Here's what I want you to also check out. I could have used like 1980, 1985, 1990, 91, so forth and so on. But that would have really dragged my x-axis really up high. And sometimes that's a little bit frustrating. So I want you to know that the x values that I have here are for convenience, but I also have to keep in mind that the x values mean the number of years after 1980. All right, so now that that has been clarified, we're going to go and do some quadratic regression by putting the following equation right into the next box. And when we do, what we get is the following graph that seems to approximate a lot of the values. We kind of knew that it wouldn't hit every point, given the fact that this isn't exactly strictly a quadratic equation, but this seems like a parabola of best fit or a quadratic of best fit. So what do mathematicians do with this information? Well, they kind of go on to answer the next couple of questions that we have here. Let me grab our screen again. And it says, use the model to predict the amount of waste produced per day in 2010. So we could probably even check this information, see if it was accurate based on what we have, because it's long past 2010. But let's go back and think about how we can do that. Remember that 0 is representing 1980. How many years transpired if I wanted to get to 2010? If I want to get to 2010, that will be about 30 years. And so what we'll do is we will write this as a function, and then we'll plug in or substitute in 30 years. So there that is, just plugged in all the A, B, and C values, made sure that it was an equation. I'm going to go down here, and now I'm going to let the calculator do the work for me by putting in f of 30. So I'm going to let the calculator do that, and it seems that the prediction, according to our equation, is that we'd have 3.38 approximately, or 3.39 tons of trash. Is that what it is? I forgot. Tons of trash, pounds of trash in terms of waste per day, per person, according to our model. So I'm going to write that down here so we can have that answer, 3.389, or maybe it was 3.3. Now I've forgotten, y'all. Let me see, 3.388. So we'll just put 3.39 there. pounds per day per person. All right, almost done, almost done. This is the last example. Use the model to predict when the amount of waste will drop to 3 pounds per day. All right, so how long will that take? We'll go back to Desmos. Let's see what we can do here. We'll just look exclusively at our graph a little bit. And basically what we're looking for is when this will drop down to 3. So what I'm going to do is actually come here and I'm going to write y equals 3. And so what that's going to do is give me a horizontal line at 3, and it'll give me the exact time that it'll drop down to 3 or below 3. So according to this, 32.6 years or 32.7 years after 1980, so we understand that to be about 2012, late 2012, the amount of trash that each person produces in the United States should reduce to 3, and any time after that should be less than 3. Again, according to our model. All right, so hopefully we can see that sometimes these equations can be quite useful. So what did we say? 2012 and after. All right, so with that in mind, guys, this is all we got for today. We need to start preparing for our test for Chapter 4. Lots of information here, all of it working together, but a lot of information to keep straight. So we need to begin studying. All right, take good care. Look forward to talking to you guys soon. Bye-bye.